Welcome back. We are into our fifth discussion on states of matter. In these discussions, what we have looked at thus far are intermolecular forces, where we are now capable of identifying the kinds of forces that exist in molecules, and we were looking at properties of gases. So, today we will continue with our discussion on properties of gases, and we will try today to get to the ideal gas equation and maybe some applications of this equation for numerical problems. Where were we when we last finished? We had looked at Boyle's law, which relates pressure to volume or volume to pressure, whichever way you want to call it. That is, PV equals constant at constant temperature and for fixed amount of gas. We also looked at Charles or Gay-Lussac's law, which relates volume to temperature, and we also talked about the Avogadro hypothesis, which relates volume to the number of molecules that are present. Avogadro's hypothesis came about as a result of the observation of Gay-Lussac on combining volumes. So, we are now trying to assemble all these together in terms of an equation of state. Gay-Lussac's law about combining volumes is something that you would have seen in your first unit of the NCERT book. So, before we go and introduce the ideal gas equation, let us try and see what is it that we are trying to achieve. What we are trying to achieve is to relate mass, pressure, volume and temperature to individual molecules in a gas. And for this, the all important thing that we need is Avogadro's hypothesis. So, before we go and look at the ideal gas equation of state, and you should also remember that when Avogadro's hypothesis was introduced, Dalton had already proposed that each atom is same as every other atom in a sample, so what it implies is that there is a characteristic atomic mass, and this is something that Dalton had introduced. Once again, you will see it in unit 1 of your book. So, in the light of the Dalton's theory, then Avogadro's, what Avogadro, so you have that the mass of the sample is the number of molecules or atoms present in the sample times the atomic or molecular mass. So, this is something that we know from Dalton's atomic theory, and what Avogadro has now done is to relate this to the volumes of gases that react after Gay-Lussac's observation. So, let us try and see if there is a model that can explain all this observation with the gases. So, this model that is proposed is the kinetic molecular model. For gases, also called the kinetic theory of gases. There are essentially three parts to this. The three parts, the first part discusses model based on the molecules. The second part of this is about the motion in molecules. And the third part of this model is, of course, Avogadro's hypothesis. So, let us look at, well, Avogadro's hypothesis anyway we have already looked at. So, we will look at parts 1 and 2 here of this model a little bit more carefully. So, the first thing that we know is that gases occupy space and are composed of molecules. Okay. The first thing that we know from this model, what it says is that the mass of the gas is due to molecules. That is, what we are saying is that if you have a gas in a container which is made up of molecules, this empty space here contributes nothing to the mass, and all the mass comes from these molecules. So, the empty space has no contribution to the mass. The second part about the molecules in this model is that the molecules occupy no volume. That is, this is important. What we are saying is, it looks contradictory and counterintuitive. What we are saying is, if you have a container which contains a gas, the molecules in that contribute to the mass, and that is all where the mass comes from. And we are also saying that these molecules occupy no volume. It does look counterintuitive. If you have, what we are saying is, we have lots of these particles. These particles occupy 0 volume, but contribute all the mass, and the space is all the volume and has no mass. And we also know the third thing that we know. So, the first thing is that the mass of the gas is completely determined by the molecules. The molecules occupy no volume, so 0 volume. And the third is that we know that from Dalton, all molecules have the same mass. So, that is with regard to the molecule. So, we said there are three parts to this which allows you to relate the mass, volume, temperature and pressure of a gas. So, we are saying that gases occupy space, it is composed of space and of molecules. And we are saying with regard to the molecules, mass of the molecules is directly related to the mass of the gas, that is, the space has no mass and molecules have no volume, and that all molecules have identical masses. So, next we go on to look at motion in these molecules. In this model. So, what we are saying is that molecules in this model, molecules are in ceaseless random motion. Okay? So, the first part of this is that we say that the molecules move in straight lines. And they move in straight lines until they undergo collisions. And they undergo collisions with other molecules or with the walls of the container. This motion in straight lines is important, because what it is telling you is that if you had an intermolecular force that exists between the molecules, then the molecules would not travel in straight lines, because the attractive force that exists between the molecules, if it does exist, will lead to a change in the path of this molecule. So, what we are saying is that motion occurs in straight lines essentially means we are ignoring the intermolecular forces that exist, which we know with that exist in real gases. So, they move in straight lines. Okay, that is very important. And once they come, so you have this motion moving in a straight line. Imagine that you have another molecule here, it travels in a straight line, although in reality it would not, because of the presence of intermolecular forces, and it goes and it undergoes a collision. If it is head on, it goes right back. If it undergoes a grazing collision, it will collide here and it will move off. So, each of these things goes in straight lines until it undergoes collisions either with the walls of the container or with other molecules. That is the first part of this, what kind of motion these molecules exist in this model. The second thing is the motion is random with respect to both the rate and the direction. What we are saying is the molecule could have speeds. When we are saying that it could be random with respect to rates, what we are saying is the rates of the molecule. So, you are taking a sample of a gas which is composed of lot of molecules, and the first part has said that these molecules have all the mass, and this space that is there contributes nothing to the mass. There is a lot of empty space in it, and what we are saying, each molecule could in principle have speeds that range from 0 to very high values. And it is random with respect to, that is, if you took one molecule, you won't know what its speed is when you looked at it, and one molecule and another molecule could in principle have completely different speeds. And they are also moving in random directions, which means that if one is moving in this direction, another one could be moving in a completely different direction. So, both in terms of speed as well as in terms of direction, the motion of the molecules in this model is random. So, over all possible orientations, the molecules could move. The third thing that we say in this model, and this model is due to Rudolf Clausius, whose name you would associate with later when you study thermodynamics and entropy if you do. So, this was proposed, this model was proposed by Rudolf Clausius in 1857 on the basis of the experiments that were done, that we discussed about Boyle and Gay-Lussac, etc. Okay. So, the third piece of this model with regard to motion, we say, is that the kinetic energy of the molecules in the sample varies with time. Also, at any temperature, the average kinetic energy per molecule is the same for all molecules in all gases. That is important. And that the temperature is proportional to the kinetic energy. So, there are three parts to this, right. So, if you took a molecule, so imagine a sample with, for convenience, imagine that there are 4 kinds of molecules. One is a black one, another is a blue one. We have a third molecule which is green, and a fourth molecule which is red. And these 4 colors are not for 4 different types of molecules, it is the same gas with, and I have just colored them differently to tell you that they could in principle have different velocities. So, each color represents a different speed. And also different direction. So, it essentially means, since velocity has both speed and direction, what we are saying is they could be moving in completely random orientations. That is some way of looking at it. Well, we have too few molecules, and what we are saying is the kinetic energy of each of these molecules could in principle vary with time. And you will wonder, how does that happen? It happens because when it undergoes a collision, and this is part of the fourth thing, which says that there is conservation of energy. So, what this means is that when 2 molecules collide, so imagine that we know that the kinetic energy of a molecule is of any of a particle with mass m is given by half mv square. So, each of these velocities are different. So, call them v black, v blue, v green, and v red. And we are saying that each of these could vary, the speeds could vary which is the magnitude of the velocity. So, the speeds could vary from 0 to a very large value, completely random, and we are saying that the kinetic energy of the molecules could vary in time, which means that if a black molecule, a molecule with a velocity Vb collides with a molecule with this V blue, what could happen is there could be a redistribution of energy, and when that happens, V blue will no longer be what it started off with before the collision. So, there is energy conservation, which means that half m V b square must equal, so plus half m V blue square equals constant. So, when it undergoes a collision, there is a redistribution of energy that could happen between the two molecules, and this is what we call an elastic collision. And the problem with this elastic collision is that it is a very ideal thing. So, you cannot make any model in reality to satisfy the kinetic theory of gas, because any two things that you take, if you had two balls and you undergo a collision, then obviously it is not elastic. So, this is a very idealized model for which it is very difficult to imagine a mechanical analog which would work, because all collisions that we have in reality are not elastic, right. So, the third postulate about the kinetic energy is especially important. This is more or less something that we have come to accept. What we are saying is the kinetic energy of each of the molecules varies with time, and this variation could come as a result of collision. And we are also saying that at any temperature, the average kinetic energy is the same for all molecules, for all gases, average kinetic energy. So, if I have to calculate the average in this particular case, I will say half this, which is represented either as in this way. So, this is average kinetic energy. So, I say I would write it either like this, or K E bar is half m V black square plus V blue square plus V green square plus V red square divided by 4, because I have 4 molecules. So, if I have large number of molecules, I do this summation over all the molecules and divide by the total number of molecules, and that will give me the average kinetic energy. This is something that we do if, for example, if you are a cricket lover or if you are a football lover, whatever it is, you look at Virat Kohli, for example. We say that he has, over all the 1 days, he has scored this many runs. So, for example, in ODI 1, if he scores 10, or I guess with Virat Kohli it should be more than 100. So, let us make it 105. In the second one he scores 72, in the third that he scores 88, and so on, and you find the average of this, and you say the next time he comes to bat, we expect him to score typically around the average. So, the same thing what we have done, and so we say that if you took this divided by 3, that will give you the average, and the total runs he has scored is 3 times whatever the average is. Similarly, per molecule I have redistributed the energy. Some of them have large kinetic energy, others have small slow kinetic energy, but the average kinetic energy of the molecule is just this. So, each molecule you can imagine has got that much average kinetic energy, and I have n types molecules. So, it will be the same, right. So, we have that the average kinetic energy is the same for all molecules of all gases. That is important. So, if I took gas, let us imagine that this is air, and if I took another sample of, let us imagine this is methane, at the same temperature, keep the temperature the same. Now, what we are saying is that the average kinetic energy of both of the molecules, all the molecules in both air as well as in methane would be the same. And we also say that the temperature is proportional to the kinetic energy. Okay? So, there are three parts to that thing about the kinetic energy. And the fifth one is that there is, in this model, there is conservation of momentum. And what we are saying is, if m1 v1 must equal m1 v2, if we are considering the same molecule. If it underwent a collision, for example, we are saying, or this thing might be better to say that this is a constant. Right? If you underwent a collision between molecules with velocity v1 and velocity v2, we are saying that this is a constant. So, this might be a good point for us to stop and look at what are the things that we discussed in this model. So, we are saying, according to the kinetic theory of gases, we say that there are three pieces to the kinetic theory of gases. The first piece discusses about molecules. The second piece discusses about motion of molecules, and the third one is Avogadro hypothesis, which we won't have much to say because we have already gone through that. And with regard to the molecules, we say mass only in molecules. Secondly, molecules occupy zero volume of molecules. And the third part is molecules of the same gas with all have identical mass. Right? So, if you write it this way and break it up, then it's easy enough for you to remember these things. And with regard to motion of the molecules, the first thing that we say is random motion, ceaseless random motion, both in rate and direction. That is, if you have a sample, different molecules have different velocities. The second thing that, oh no, the first thing that we said is, that is not what it is. The first thing is move in straight lines. Anyway, you can just rewrite it a little bit. So, they move in straight lines and they have velocities which vary in terms of its magnitude, which could vary from 0 to a very large value. The third thing is about the kinetic energy, that it varies with time of a molecule and at any temperature. So, the third point is regarding the kinetic energy of molecules, that it varies with time for a molecule, that all molecules in all gases have the same average kinetic energy at a particular temperature. So, kinetic energy is proportional to temperature. And the fourth one is conservation of energy. And the fifth of momentum. So, that in a sense should give you a way of easily remembering the different parts of the kinetic theory of gases. Now, what does the kinetic theory predict? Some of the things, the predictions, whether it agrees with experiments. So, the first thing that we look at is what is called absolute zero. Oh, and that's something very interesting in this kinetic theory. So, what we are saying is it appears to be counterintuitive that the molecules occupy zero volume, but the gas occupies space. The best analogy you can think of is a ceiling fan, the closest analogy. The ceiling fan, when it is static, has a volume which is determined by the volumes of the blade, and because the blades are essentially flat, the volume is very small. But the moment you switch it on, the effective volume occupied by the fan is much bigger than the volume of the three blades put together. So, that is essentially in a sense what we are talking about in this case. We are saying that the volume occupied by the molecules is 0, unlike the fan which is small. Here we are saying that the volume occupied by the molecules is 0, but the space that it takes up is determined by the space, the volume of the container, which means that all the space that a gas occupies, that the gas molecules occupy, arises as a result of motion, right. Now, we also know that from, if you remember, when you looked at volume plotted as a function of temperature, when you did this with Charles' law or Gay-Lussac's law, there was a straight line and it intersected the, where I have plotted temperature in degrees Celsius, it intersected the x axis at a point here which is minus 273.15 degrees Celsius, and this corresponds to 0 volume. So, this is 0 volume. And according to the kinetic theory, what we are saying is all the volume that a gas occupies arises as a result of motion. And at this temperature, from Gay-Lussac's law, we are saying that the volume goes to 0, and we know physically that the volume cannot be negative. Volume has to be greater than or equal to 0, and we are saying that the volume arises completely from motion. So, what this means effectively is that at this temperature, so at this temperature where volume is equal to 0 implies that there is no motion, and this point where the volume goes to 0, the temperature at which the volume goes to 0 is called the absolute 0, because volume has to be greater than or equal to 0 and kinetic energy or the motion has to be greater than or equal to 0. So, you can't go for any system go below this temperature, and this temperature is called the absolute 0, where there is no motion. So, the kinetic energy is 0. And for a gas at this temperature, the volume is also 0, because the volume is only related to motion. So, effectively, if, well, for practical matters, if you are given temperature in degrees Celsius. If you have to go to temperature in Kelvin, what we are saying is we add 273.15 plus temperature in degrees Celsius gives you temperature in Kelvin. That is for practical matters, but there is a deep physical significance. This is a very easy practical matter for you to do, and for any time you are doing physical chemistry, it is better that you always operate with temperatures in Kelvin. And converting from Celsius to Kelvin requires only you to add 273.15. Practical matter, very, very straightforward. So, at this temperature, all motion ceases, and you cannot go to any temperatures below absolute zero. So, that is why it is called the absolute zero. Okay, so that is one prediction that we have, and that we have from kinetic theory. Let us also look at the kinetic energy of the gas molecules a little bit. To do that, what we will do is we will look at two samples of two different gases. Under identical conditions. So, imagine that you have one sample with whose molecules have a mass of atomic or molecular mass m1, another sample whose molecules have an atomic or molecular mass n2. Let us imagine that we put this gas molecule, this sample which has molecular mass n1, into a container, and we have n1 molecules of this. And what we do with the second one is we put this gas in an identical size container with the same number of molecules. So, identical containers, so the volume is the same, the masses are different, but we have ensured that the number of molecules in the two are the same, and we also ensure that they are both at the same temperature. In this situation, applying Avogadro's hypothesis in the converse fashion, we say Avogadro says that if you have two gases under same temperature and pressure, the volumes proportional to the number of molecules. Because the volumes are the same, the number of molecules are the same. So, I do this in reverse. So, I have the temperature the same, the masses are different, the number of molecules are the same, I have ensured this. So, the pressure has to be the same. Avogadro converse, I write it. So, I am applying the Avogadro principle in the converse fashion. So, the pressure is the same in the two gases. And from the postulate of the kinetic theory, we know that the kinetic energy of the two samples at the same temperature has to be the same, which means that half m1 v1 square must equal half m2 v2 square, which implies that v1 square over v2 square is m2 over m1, or v1 over v2 is square root of m2 over m1. Now, the question is, in this particular case, what velocity to use, right? This is the problem. I am only saying that the kinetic energy in this sample has to be the same as the kinetic energy here, because everything else is the same by Avogadro's law, the pressure is the same, temperature is the same, and if the kinetic energy postulate is the same, then this has to hold. So, the only question is what velocity to use for this, and we will suppose that the average velocity by that postulate is the same. So, we say that half m1 v1 bar square. So, this corresponds to the average velocity. Average velocity of the molecules in sample 1 must equal this. We are just supposing, and this would be a prediction. And so, we are saying V1 bar over V2 bar must equal root M2 over root M1. Is there a way to test this? Testing this would be difficult because it is possible that you will not find any molecule which has average velocity equal to V1 bar. That is something that you have to realize, right. If you have used the Virat Kohli argument, when you take an average, you will get, for example, Virat Kohli's average is some 52.32. It is impossible that he will ever score in any innings 52.33 or something like that. The same thing applies here. It is possible that there are no molecules whose velocity is V1 bar. On an average, we are saying that is the velocity, right. But there is a way of doing this. You look at the collision frequency. So, if you take the molecules, the gas molecules in a container, the collision frequency in one is related to the velocity, the average velocity that you have of the molecules in that sample is related to the velocity. So, V1 bar over V2 bar must equal the collision frequency. So, what we are saying is the number of collisions, that if you have lot of molecules in here and the average velocity is higher, the number of collisions that it has with anything will increase. So, we are saying that the proportionality, there is a proportionality between the collision frequency and the velocity, and so V1 bar over V2 bar is equal to the collision frequency in sample 1 over the collision frequency in 2. And if you take the collision frequency per unit area for the same area, or per unit area if you took, they are again the same. So, if I took the same area, it does not make a difference. Now, this gives you a way, and we are saying that this is equal to root M2 over M1. Why do we do this? The reason we are doing this is the following. So, imagine I have a sample here and which has gas molecules, and I have a small area here, and we are saying what is the number of collisions that we have with this small area, and we are saying that the collision frequency that will depend upon the average velocity that you have here. So, if I have two different samples, I can do this. So, this area. Now, how do we measure this? So, there is a way that you could measure this. So, you take a spherical thing and you make a small opening here and you collect the gas here. So, the amount of gas that you get out here will be proportional to the number of collisions that the molecules has this with this area, right. Because you have this sphere, you have a small hole at the wall, and the number of molecules that you collect at the other side will be proportional to the velocity. And if you have two different samples with the same area, the volume that we collect here will be proportional, and we do it per unit time or whatever you want. Amount that you collect here will be proportional to the velocity that we have here, right. And this is an example of what is called an effusion experiment, right. So, this is effusion experiment, and what we can then do is the volume of gas collected will then be related to the molecular masses. So, you can confirm this whether the kinetic theory of gases is correct by doing an experiment which is called an effusion experiment, and this was done by Thomas Graham, and it is called the Graham's law of effusion, which does not figure in your syllabus, but you can easily work out. So, you can work out that the collision frequency is proportional to the inversely proportional to the mass, which you can then relate it to the density, and so this is what is called the Graham's law of effusion, where you compare two different rates of effusion. So, effusion is when you have something coming out of a small opening, and this is called the Graham's law of effusion, which you could show that the amount you will get is related to the densities, the square root of the density is inversely related to that. And so, this is a confirmation of the kinetic theory of gases. It is not something that is part of your syllabus, but it is easy enough understood for you. Okay. Now, at this time, you can also relate the temperature and the pressure. So, the pressure that a sample exerts on the container is related to the number of collisions that the molecules in a sample make with the walls of the container. Per unit area, per unit time, per unit area, per unit time. Now, how will we proceed? We know in this model that each molecule has a velocity. So, all that you have to do is how much the momentum changes per collision. Since the derivation is not important to you, but you can understand how it goes. Imagine that a molecule comes with a velocity v1, it strikes this. So, it comes with m1 v1 and it goes back, and so the total change in momentum will be 2 m1 v1, and you can do this per unit area, per unit time, and you can relate the pressure. And because we are saying that the average velocity is related to the temperature, you can relate the pressure with the temperature, and because we already know that at absolute 0 the motion does not exist. So, we have a relationship between pressure and temperature. The derivation is not important and neither is it part of what you are discussing, but you can understand where it comes from. A molecule comes, it strikes the wall, the change in momentum is the force. So, force is related to the change in momentum, and force per unit area, and you have to do this per unit time, and this per unit area will give you the pressure, and you can relate how much momentum change. And since the velocity is related to the temperature, we can say then the pressure is related to the temperature, and this is how one goes about it. So, although I intended to get to the point where I would derive the ideal gas law, so these are things that we already know from the kinetic theory of gases. So, what this allows us now is, now we can put this together. So, let us recap and also derive, or not derive, at least show very quickly how it happens. We know that V is proportional to 1 over P, and this kinetic model has worked quite well. So, the V is proportional to 1 over P, which is due to Boyle. We know that V is proportional to T. This is attributed to either Gay-Lussac or Charles. and according to the Avogadro hypothesis that V is proportional to N. Now, you put these three things together and you will say that from here you get PV equal to a constant. This is at constant T and number of molecules. V is proportional to T for all gases, say for the at the same pressure, and V is proportional to N according to Avogadro. So, if you put this all together, mathematical derivation is there in the book. We get PV equals nRT. I am not going through the derivation because it is there in the book, right. So, this is pressure, this is the volume, this is the number of moles of the gas, this is called the universal gas constant, and this is the temperature in Kelvin. Right, straightforward from these three laws, well, hypothesis or law for Avogadro, you can put together this. What we will do in the next class is to look at, well, some numerical things involving this. Maybe I will show you some demonstration there rather than give you this mathematical derivation of PV equals nRT, which is in the book. What we will look at is some sample of the data that we have, which will give you how that this is indeed true. So, that we will do in the next class, and then maybe we will look at some numerical examples of the use of the ideal gas equation of state. So, this is called the ideal gas equation of state, which we will look at in the next session. Thank you.